Hello, everyone. Today we'll talk about modular arithmetic as it pertains to quantum information topics. Modular arithmetic is a system of calculation that is centered around remainders. It has numerous applications such as an RSA encryption and in Shor's algorithm. It also makes it easier to answer questions such as, is 3 to the 5 million and 1 plus 9 divisible by 8? Or show that if we know that the sum of the digits of a number is divisible by 3, then the number is divisible by 3. For example, for the number 2547, 2 plus 5 plus 4 plus 7 gives 18, which is divisible by 3. So 2547 is divisible by 3. The notation for modular arithmetic is as follows. Given integers a and b and the natural number m greater than 1, the equation in the black box is read, a is congruent to b modulo m. What this means is that if you subtracted b from a and divided the expression by m, you get an integer n. If we rewrite this way, assuming a is greater than b, this means b is the remainder. This is an example using the notation. 11 is congruent to 6 modulo 5. If we subtract 6 from 11, we get 5, which is divisible by 5. Here's another one. 3 minus 29 is minus 26, which is divisible by 2. Let's now look at some properties that can help us do this kind of arithmetic. Property 1 states that if a is congruent to b modulo m and b is congruent to c modulo m, then a is congruent to c modulo m. 2. If a is congruent to b modulo m and c to d modulo m, then you can just multiply the corresponding sides of the equations and the result will still be congruent modulo m. Point 3 has the same idea but with addition. Point 4, which involves powers, can actually be proven from point 2 and by using mathematical induction. In 5, it states that you can multiply both sides of the equation by an integer and still maintain the relation. And finally, in 6, the relation is maintained by adding an integer to both sides. So now, why don't we solve a problem together in which we'll use a lot of these properties? Let's go back to this problem that we discussed earlier. Is 3 to the 5 million and 1 plus 9 divisible by 8? Let's start with this equation. 3 squared is congruent to 1 modulo 8. Using property 4, we raise both sides to the power 2.5 millions and simplify both sides. Then, using property 5, we multiply both sides by 3. Property 6 allows us to add 9 to both sides. Then, using property 1, since 12 is congruent to 4 modulo 8, we get this. Notice that the remainder is 4, not 0, so no, 3 to the 5 million and 1 plus 9 is not divisible by 8. This is a much easier way to find this out compared to fully evaluating the expression first. Now let's talk about possible values for the remainder when an integer alpha is divided by a natural number m. Well, the value of the remainder will be between 0 and m minus 1. Notice that this is a finite set, even though the set of integers is infinite. A consequence of this is that if we keep dividing one integer after another in order, the values of the remainder will repeat themselves. Let's look at the example when m equals 4. We will start with alpha from 0 to 16, each time computing the remainder upon division by 4. 0 divided by 4 gives remainder 0. 1 divided by 4 gives remainder 1. 2 divided by 4 gives remainder 2. 3 divided by 4 gives remainder 3. 4 divided by 4 gives remainder 0. 5 divided by 4 gives remainder 1. Similarly, 6 gives 2, 7 gives 3, then next one 0, then 1, then 2, then 3, then 0, then 1, then 2, then 3, then 0, and so on. If we color code the repeating pattern, we get this. Notice that the pattern repeats for every 4 integers, so the period here is 4. The relationship between m, alpha, and r can be written using modular arithmetic this way. So, if alpha is the quantity we keep increasing by 1, this will make r a function of alpha for a given m, and it's going to be a periodic function. In quantum information, a function called the modular exponential function, which is important in Shor's algorithm, is defined in a similar manner to how we define r here. In today's exercise, I would like you to use what you learned about modular arithmetic to prove that if the sum of the digits of a number is divisible by 3, then the number is divisible by 3. مع السلامة.